Welcome to the next lecture of Software Design and Modelling, which I've somewhat whimsically titled Design Principles Laughing in the Face of Change. So the idea of this lecture is that we're going to look at what we mean by a good design. In other words, when we choose a design for our software system, what are we trying to achieve? We're going to do a quick review of some basic design principles, which I hope you already know from Inf 2. And then we're going to go a bit further and we're going to discuss a collection of design principles known as the solid design principles. And after that we will begin to think about design patterns and why we might want to know those. Well, what are we trying to achieve when we choose a software design? Of course, we're trying to achieve all the good things. We're trying to achieve all the things that we would like to get from our software. Fundamentally, we want to be able to build software faster, cheaper, better. But as I advertised earlier in the course, overwhelmingly what this basically amounts to is that we want our designs to be resilient in the face of change. Remember, that was what was going to allow us to say we'll use our prowess with software design to address the fact that software requirements management and software maintenance are such wicked problems. So what kinds of change are we talking about? We're talking especially about changes in the requirements of our software system, and those might be functional requirements or non-functional requirements. And perhaps in this context, non-functional requirements also encompasses constraints such as the different software components that your system has to interoperate with, and in that way it's going to cover not only problems that might arise in the requirements capture stage, but also the problems that typically arise during the maintenance of a long-lived software system. So as we said before, resilience in the face of change was the main motivation for using object orientation in the first place. So I think the most convincing reason for the success, the enduring success of object orientation as an approach to structuring software systems, is basically that if you structure the system in a way which mirrors the structure of the domain, and so the terms that appear in your system design match the terms that appear in descriptions of the domain in which the software has to operate, this tends to make the structure likely to be stable as the requirements change. So the focus here is mostly on localizing change. So we accept that requirements are going to change from time to time, and what we're looking for is being able to change the software easily. Well, what is it that makes a change that you might have to make to a large software system easier than some other change? Okay? It's never going to be impossible to change the software to match your requirements. What is it that's going to make it easier than it might otherwise have been? Well, perhaps the most obvious thing to look for is that the amount, if you like, the number of lines of code you change shouldn't be too many. Okay? And so that amounts to saying we would like to minimize knock-on effects of a change that you make. We would like to avoid situations in which you change one line that makes the real important interesting change to your software system, and then you discover that for silly reasons, because there's a lot of coupling in your system, you also have to make changes in a dozen other places in the system. Okay? That would be a sign that the one line you changed was coupled to all those other places in the system, and we are trying to minimize the extent to which that happens. We're trying to have low coupling in the system. But we also need to be able to identify easily what it is we have to change. Okay, so we want to keep our design understandable and clear, especially bearing in mind that it might happen that change has to be made as part of the maintenance process, and that might mean that it has to be made by somebody who wasn't involved in the original implementation of the system. They have to be able to come along and understand your complex, powerful system and nevertheless understand exactly what they have to touch in order to change it to meet the changed requirements, and that's actually really hard. The other thing we want is that even for a fixed number of changes that we might have to make in our system. Suppose we say, okay, we accept that we're going to have to change 12 lines of code in our system. Not all changes to 12 lines of code are equally disruptive or equally difficult to make. it tends to be much easier to change 12 lines of code within the same class than it is to change one line of code in each of 12 different classes. Now, why is that? Now, partly it's just for sheer practical reasons. If you've got to change code in a variety of different classes, you've got to find them all. Okay? Each time you've got to load it up into your editor, you've got to find the place you have to change, you've got to check that you've done it right, and actually that there's a certain amount of economy of effort in having as many of those changes within one file as you can. Okay, or close together in the code in some sense. But in a serious mission critical, especially software system, it might be even more important than that, because you might have some important quality control processes that have to be gone through every time you change some particular unit of your system. You might say every time you change a class of this system, we have to go through a design review process and a testing process and a verification process and what have you for that particular class. Okay, and it might well be that that is an effort which is more or less independent of the actual number of lines of code within that unit that have changed. So you might find that actually, roughly speaking, if you change one line of code in each of 12 classes, you've got 12 times as much effort to go through than if you had changed 12 lines of code that all occur in the one class. You see what I mean? So all of these things are things we're looking for. We're trying to have high cohesion, which is to say, when something realistic changes in the real world, we would like all of the affected code to be nearby, and that amounts to saying we would like the code to be highly cohesive. So we are already starting to see some of these pieces of terminology, which I hope you already know from Inf2. If not, by the way, it may be that I'm out of date with exactly what was taught in the version of the Inf2 course that you did, then please do look them up. I'm going to go briefly through them here, but these things I am basically assuming this is just a recap of. I'm assuming you already know this stuff. So if not, go away and look it up. And by the way, please tell me so that I can update the course in future. Okay, so high cohesion, we already talked about, amounts to saying nearby pieces of code, for example lines that occur in the same class, should in some reasonable logical sense belong together. Okay, so this amounts to things like, if you've got a class, it should be doing sort of notionally one job. It shouldn't be doing 3 or 4 kind of more or less logically unrelated tasks. That would be to have low cohesion. We're looking for high cohesion, where things that your stakeholders, the people who understand your domain, think of as being closely related, actually occur close together in your software system. We're also looking for low coupling, and again we also just mentioned that, where we're trying to say there should be as few dependencies as possible between different parts of your system, and the further apart the parts of the system that we're looking at, the rarer it should be for them to have dependencies between them. Now, you can't of course eliminate dependencies, because that's what makes your software system powerful in the end. If you had no dependencies at all between parts of your software system, you'd actually have 2 different software systems, and if you can have it, that's great. Okay, but we're trying, other things being equal, to have high cohesion and low coupling. Modularization is partly enabling that and partly helping us to understand how the software system works. And at its most basic, that just means that there are modules in the software system. The software system isn't implemented as one ginormous class. It has a whole bunch of different classes that are working together. Maybe one thing that's worth pointing out here is that sometimes people reckon they can get high cohesion and low coupling by only having one module. And in a very superficial and artificial sense, that might be true, in the sense that if you measure your cohesion by saying, are the things that go together all in the same module, then of course if there is only one module, then the answer to that will be yes. And if you say you measure coupling by saying, whenever you have 2 modules, is it the case that they don't depend on one another, then if you can never have two modules because there is only one module, then the answer to that will always be that you have low coupling. Okay, but that's not a useful sense in which to have low coupling and high cohesion. Okay, so these things work together. Okay, you have to have sort of modules that make logical sense, and you want each of those to be highly cohesive, and you want the collection of them to be as uncoupled as possible. And it's because of artificial ways of achieving high cohesion and low coupling like that we can't just say this is a thing that can be straightforwardly achieved by an automatic transformation of your design, okay, because it would be quite difficult to encode the that's cheating sense of the non-solution I just described. So this is essentially, it's about human understandability of the design, really, and these are essentially human-focused properties. We'll take abstraction and encapsulation together, and just a word of warning, these terms get defined differently by different authors. The distinction that I like to make between them is that to say, if we say our module offers a good abstraction, then what we're saying is, in order to use this module, in order to write a client of this module, you do not need to understand the details of what's inside it. In particular, you do not need to make your client depend on details of what's inside the module. Okay, if that's the case, we're going to say that the module has a good, or sometimes even provides, okay, a good abstraction. And this amounts to things like saying, well, okay, what does this module represent? If it represents a customer, say, then what API should a customer offer? Okay, what services should you be able to request of a customer? What methods should you be able to send it? What should you expect it to do? And it's a good choice of those things that gives you a good abstraction, because if those things are well chosen, then clients expect to be able to just use those facilities that you've chosen. They don't expect to have to delve into the internals of the module in order to understand precisely what it is that each of those things does, and to implement something slightly different that they might want. Okay. Encapsulation goes one step further and enforces the use of the abstraction. Okay, so this is when you say not only can you use the module via its abstraction, but you must use it via its abstraction. So the classic case here is that it's conventional that an object-oriented class will provide only methods as part of its public interface. It won't give direct access to the data that is held within each object. We say that the data is encapsulated. Okay? So at the most basic, when you write a class in Java, you should normally expect to say the attributes within your class will be private. Okay, you should only make the attributes in your class not private if you have a very good reason for it, and there aren't very many of those very good reasons. Okay, and then the last one is a separation of interface and implementation. We really are talking about a notional separation of interface and implementation here, and this very much goes with the stuff I've already been talking about. It says you should be able to read the interface of a module without needing to read the implementation. In some programming languages and some systems, the interface is physically separated from the implementation. So if you are used to programming in C++, for example, you'll be used to seeing a .h file that specifies the interface to your class separate from your .cc class, which gives you the implementation of it. Java doesn't do that for rather interesting reasons, but the notional separation is still there. Okay, so those are the principles that I expect you to know and understand already coming in. So that was a bit of a whistle-stop reminder. Now we're going to go a bit further than that and look at the so-called solid design principles. So the acronym SOLID was coined by Robert Martin, Bob Martin, Uncle Bob, who has written a lot of very good stuff about object-oriented design on the internet. I encourage you to go and read almost anything he's written. The principles that he was naming here were not developed by him. They were developed by many people, and at the time that he coined this solid acronym they were pretty well understood, and what he was doing was bringing them together and saying these 5 are particularly important design principles to understand if you're going to produce a good object-oriented design, and here is a catchy acronym to help you remember the 5 of them and that they go together. So you want a solid design. Okay. So each of the design principles has its own 3-letter acronym, and we will basically go through them one at a time. But there's also some required reading, I think, so don't expect to necessarily absorb them fully just from what I say here. There is also some reading to reinforce it. So let's have a look at the single responsibility principle first of all, the SRP. So this very much goes along with what I was just saying about wanting our modules to be highly cohesive, because what we're saying here is that a class should be one thing and be one thing well. So we sometimes think about doing one thing and doing one thing well, but since classes are representing entities, I think the be one thing is perhaps a better way to put it. What do we mean by a thing, really? Well, people put this in different ways. I think you can think about it as being a core responsibility or a kind of responsibility. The things that your class does should go together so well that you can really say there's a single responsibility that your class has. Remember that when we talked about CRC cards, we talked about being able to write a one-sentence description of what the job of the class was. Well, that captures the idea that you should have one responsibility rather than a list of disparate responsibilities. Bob Martin talks about this as being having a single reason to change. So it's essentially about coherence. The idea is that your class might offer several different operations, but they should be related enough that in practice, if there's a requirements change that's likely to make you have to change the interface to one of those operations, it's likely to have to make you change all of them. Okay, they go together. The open-closed principle is sometimes a bit difficult to get your head around. So this goes back to Bertrand Meyer, whose seminal programming language Eiffel was never terribly widely adopted, but was very influential on software design in general, and later object-oriented programming languages in particular. So he wrote that software entities, including classes, modules, functions, whatever, should be open for extension, but closed for modification. And fundamentally what he meant by that was that you should be able to modify or extend the behaviour of a class without necessarily having to modify its code. And the classic case of that in object-oriented design is that you can create a subclass. Okay? If you decide that in your application you want a thing that's awfully like that customer class that somebody implemented, but your customer class is going to be a bit special, then you don't have to do what before object orientation might have been the obvious thing to do, copy and paste the customer code and change it a bit. Instead, you can leave the customer code exactly as it is and create a subclass. And this has all kinds of advantages. For example, it hopefully means that if somebody else comes along later and fixes a bug in the customer class, then your extending special customer class will automatically inherit that new bug fix, instead of you having to sort of keep track of the fact that there might be newly discovered bugs in code that you copied and pasted. There are various different historical flavours of this principle. So if you think I'm not being very precise about what the open-closed principle really says, you're right, and it's because different people mean slightly different things by it. You could have a look at the Wikipedia page for the principle if you want to delve into that a bit more. The Liskov substitution principle, it will come as no surprise, was originated by somebody called Liskov. So this is Barbara Liskov. And fundamentally the idea here is to capture what we mean by saying that an extending class is in some sense reasonable. Okay, we know that in object-oriented programming languages it's possible to override methods so that they do entirely different things. Okay, you can take a customer class that provides a method, get account number, and you can override the get account number method so that it, I don't know, deletes the entire content of the hard disk. Okay, but that would be bad, right? So how do we capture the idea that that would be bad? We're trying to get at the idea that you should feel free to add functionality or re-implement it in a way which respects the original intention of the functionality but is now adapted to your extended class. But you shouldn't break it. What do we mean by don't break it? Well, we're really trying to capture the ISA idea of class inheritance, in the sense that if you have a client of your class which has been thoroughly tested and is known to work with all objects of the existing base class, so if I have a bank client which has been thoroughly tested with my customer class, okay, then we know that according to the way that object-oriented programming languages work, a method of the bank class which expects to be given an object of class customer can in fact at runtime be given an object of any subclass of customer. Okay, this is polymorphism, object-oriented polymorphism, and it's a feature. Okay, it's nice. It means that clients can smoothly work with objects whose most precise class is actually something that wasn't even invented at the time that they were conceived. But that power also carries danger, okay? Because our owners of our bank application are going to be seriously unhappy if, having tested their application thoroughly with the customer class, it then later on transpires that when they're given a special customer object and they invoke the, whatever I said it was, the getAccountNumber method, they find that the entire contents of their hard disk are deleted. Okay? And why would that be a problem? It would be a problem because the special customer class has overridden behavior of the customer class in a way which was unreasonable. So what we're trying to say here is really testing your client with the base class ought to suffice to ensure that the client will still work even if it's given an object of the subclass. And the beauty of the LSP is that it gives a formalizable way of capturing what it is that ensures that that will be the case. So here it is more precisely. There are a bunch of different formulations, and if you go back to the original papers, it's not always all that easy to see what's going on. But I think on this slide we have everything that you need to know, and hopefully I can make it make sense to you. So suppose we have a type. Remember that in object orientation we can think of types and classes as being almost the same thing. And let S for subtype be a subtype of T. So perhaps T is our customer class and S might be our special customer class. Okay. Now what we're saying is, if we have some property, let's say phi of x, which is supposed to hold for all objects x of type T, okay, so in our case phi of x might be the banking application works properly when you give it object x. Okay, so the banking application works properly when you give it any object x of type customer in our case. Okay. Then also phi of x holds for all objects x of type S. So in our example case, the banking application should also work correctly for any object x, say, of type special customer. Okay. Right. Now, the original formulation, which is what ensures this, is to say if for any object of the subtype there is some object of the type such that for all programs P that are defined in terms of the original type, the base type, the behavior of P is unchanged when the original object is replaced by the object we were trying to find a substitution for. Okay. So what we're saying here in our specific case is if we if you can take any object of type special customer, and we can say, whenever we have a client which is defined in terms of customer, we can find some customer object which will behave exactly the same way as the special customer object we started with in that client that was written in terms of customer. Okay, so that will rule out bad cases like our special customer operation that deleted the contents of the hard disk, because there was no object of class customer that deleted everything on the hard disk. Okay. The subtlety that's going on here, and the reason why we have to be really careful about this, is that of course we don't want to say for all clients there'll be some customer that behaves the same way as the special customer, because presumably there's some reason why special customer is special. There was something that you wanted to actually change about it. So there are probably also clients out there that are actually written in terms of special customer that, I don't know, access some extra data that special customer objects have and customer objects don't. Okay, and that's perfectly fine. But what we are trying to say is that if we're talking about clients which are written in terms of the base class and which are therefore not deliberately accessing anything that's special about the new subclass, okay, then those clients, if they're thoroughly tested for all objects of the base class, the behaviours that you see, the set of behaviours that you see when you look at all the different things those clients can do for all the objects of the base class, that should already cover all the behaviours of the client that you can see when you also use them for all objects of the subclass. There are no new behaviours of the client that arise when you try out the client on all the objects of the subclass. Okay, and I hope that if you think about it, you can see that this is actually what we want in order to make sure that our subclass is not breaking existing clients, which is a very useful thing to have. So this is a test when you're writing a subclass, is basically to say, am I doing something which is going to break existing clients? Now, there is a problem here, because we've slipped from breaking existing clients into behaviour being unchanged. Okay, now behaviour being unchanged is much stronger than the idea that that the behaviour shouldn't be broken, because what it does is it says the behaviour mustn't be changed, you know, even in some trivial, unimportant detail that nobody would ever dream of relying on. And that can be unfortunate. It can mean that in practice you may find that perfectly reasonable inheritance relationships don't in fact obey LSP. Okay, but the thing is that unless you actually have a proper contract-based specification of what clients are supposed to be able to rely on, you can't do any better, because if you don't specify what clients are allowed to rely on about the behaviour of objects of the base class, then you can't limit what they're behaving on. They might be relying on any arbitrary detail of the behaviour of that class, even if you didn't intend them to rely on it. And that's why we end up in the LSP, in a context where we assume there are no explicit contracts, having to talk about ways in which to make sure the client's behaviour is unchanged. Okay. The interface segregation principle, it's essentially the same as the single responsibility principle, but for interfaces, and I kind of surmise that the only reason it's here separately is because it's quite convenient to have an I in the acronym. At least that's a reasonable mnemonic. That's a way for you to remember what the ISP is. And essentially we're saying the client should not have to rely on parts of an interface that it doesn't need. There should be some interface that includes kind of only the things the client actually needs. And essentially what this says is that your interface shouldn't incorporate a whole bunch of unrelated things. If there's a collection of things that a client might need without needing anything else, then that should be an interface in its own right. And of course in practice in your object-oriented programming language, you're likely to say as a result of this that you might have one class that implements several different interfaces rather than having the class implement one ginormous interface that has the methods that occur in all of them. and that's a better design, because then if you've got a client that doesn't need all of the facilities that the class offers, you can have the client written in terms of just the interface that it does need to rely on, and that gives you more flexibility in future and also makes it easier to understand what's really being relied on. And the final one is the dependency inversion principle, and this says that high-level modules should not depend on low-level modules, both should depend on abstractions. And another way of putting it, it's essentially the same thing, is to say that abstractions should not depend on details, details should depend on abstractions. Now, you might think this is obvious, but it's remarkably easy to violate if you go into thinking about your software design in a sort of top-down successive refinement process, because you might well start off thinking, for example, that I'm going to say, well, you know, there should be, I don't know, some printer in my system and some print monitor component, and then you gradually split it down and down and down, and you end up saying, you know, my printer has to have, I don't know, a USB interface to my computer or something. And if you've just done it by kind of calling methods all the way down, even if you've got a sort of what looks like a beautiful abstract interface at the top, you end up saying that actually if some tiny detail at the bottom changes, everything above has to be at least recompiled and possibly, you know, probably not changed, but at least recompiled. And this is not a good idea. So what you're essentially do instead is we insert an interface which says something like, well, what is it to be a printer? A printer is a thing which can do this, this and this. And that means that clients can depend on the printer interface. They say, I don't care what printer I've got, I just want something that can do this, this and this printing stuff. That's clients depending on the abstraction. And then actual concrete printers can implement that interface. In other words, they depend on the interface. Okay, and that way the interface actually acts as a kind of narrow gate, managing any potential dependency between the client and the implementation, which is a useful thing. That will be clearer, I think, when you do the required reading. And I'll stop there for a moment.